We will now take a brief look at organic reactions. Initially, one finds there's an infinite number of possible combinations of carbon. Therefore, there must be an infinite number of reactions. How is it easy to understand such things? First of all, organic compounds are characterized. There are a limited number of types of compounds. Although not exhaustive, so far we've learned about alkanes, alkenes, alkynes, alcohols, aldehydes, ketones, carboxylic acids, and amines. Also, there's a limited number of types of reactions. You will see you can have what's called a substitution, an addition, an elimination, or a condensation. And only certain types of compounds undergo a different type of reaction. So by the end of this talk, you will see it's actually quite simple to categorize what types of compounds will react in what manner. We will start by looking at a substitution reaction, where you literally replace one thing with another. Substitution reactions are primarily undergone by alkanes. The reactants are alkanes and a halogen, R and X2, and the products are what's called an alkyl halide and a hydrohalogen, Rx plus HX. As an example, we look at propane reacting with chlorine. One of the products is HCl. However, as propane has two unique positions, there are two possible outcomes. You could either make one chloropropane or two chloropropane. The question is, which one predominates? The answer lies in something called a mechanism. If you look at the structures of propane and chlorine, you realize hydrogen is more electronegative than carbon. Therefore, the hydrogen will leave as a hydride ion to attack the chloride, and one of the chlorines will come in as a Cl- to attack a carbon with a positive charge. This is what is called an intermediate carbocation. From our previous discussion of amines, the same thought holds in terms of substitution. You can have a primary carbocation where the carbon is attached to two hydrogens and one group, a secondary carbocation where the positive carbon only has one hydrogen and two organic groups attached to it, or a tertiary carbocation where your positive carbon has three different organic side groups attached to it. As you recall from the previous discussion, more substitution leads to what's called steric hindrance, or clutter around the reactive site. And in terms of reactivity, a primary carbocation is always much more reactive than a secondary, and a secondary is more reactive than a third. So in our mechanism, the most reactive spot would be on the end, and the preferred product would be 1-chloropropane. You can also perform a substitution reaction where replacing one thing with another, with alkanes as mentioned, where your reactants would be an alkane and a halogen, and your products are an alkyl halide and a hydrohalogen. Also, substitutions can be performed with alcohols, where your reactant is an alcohol and a hydrohalide, ROH and HX, and your products become an alkyl halide and water, RX and H2O. This time, we will look at the reaction of 2-propanol and HBr. In this case, the answer to the reaction is much easier to see. The alcohol has an OH, and HBr will donate an H+. So one of your products will be water. You will take away an OH-, leaving a carbocation that the Br- will attack. So your products will be 2-bromopropane and water. A big hint to make organic chemistry easier: if you see a reaction where you can make water, make it, and then put the two other pieces back together. So we have seen substitution reactions, which occur with alcohols and alkanes. We replace one thing with another. Another type of reaction is an addition, where, as the name suggests, you simply put something into a molecule. You can have two types of additions. The first type is called a symmetric addition, where your reactants, in this case, are an alkene, a double-bonded carbon, and a halogen, R double bond R and X2. The product is an alkyl dihalide, RX2. So if we look at the reaction of propene with chlorine, the product would be 1,2-dichloropropane. How this occurs is as follows. As you see from the detailed structure of propene, there's an exposed double bond between the carbons on the end. These are bonded together by 2 electrons. The chlorine is also bonded by 2 electrons. Essentially, the double bond opens up and the bond between the chlorides open up. Each side is still donating 1 electron each, and you wind up with 2 carbon-chlorine bonds. So we have seen substitution reactions, where on an alkane or an alcohol, one part of the molecule can be replaced with a halogen. And also, an addition reaction, where a double bond is opened up. We've seen a symmetric addition. There's also an asymmetric addition. In this case, your reactant is still an alkene with a C double bond C, but now you have a hydrohalogen, R double bond R, and HX. The product will be an alkyl halide, RX. So for the same molecule propene, reacting with HCl, you have an H to go on one side of the double bond and a Cl to go on the other. The question is, which side does the chlorine go to, carbon 1 or carbon 2? This is answered by something called Markovnikov's rule, which states, in an asymmetric addition with an acid halide, the halide ion will attack the least saturated carbon. A simpler translation of that is that hydrogen likes hydrogen. If you look at the detailed structure of propene, you will see that carbon 1 has 2 hydrogens on it, while carbon 2 only has 1 hydrogen. Therefore, according to Markovnikov's rule, since hydrogen likes hydrogen, the hydrogen from the HCl will attack carbon 1, and the chlorine will attack the carbon with the least numbers of hydrogens on carbon 2. So your product will be 2-chloropropane. So we have seen substitutions, in which alkanes or alcohols can have an H replaced or an OH replaced with a halogen. Additions, where a double bond is opened up. A third type of reaction is an elimination, where again, descriptively, you are taking something out of the molecule. The reactant is going to be an alcohol, and it will be what is called acid catalyzed. The product is an alkene. So if you look at 2-propanol, where the catalysis, the hydrogen is shown over the arrow, your product is 2-propene. How this works is as follows. In the detailed structure of 2-propanol, the H plus will from the acid catalyst will obviously attack the OH minus to make water. This will leave a secondary carbocation. The carbocation has a positive charge. However, there is a negative charge right next to it. That would be the 2 electrons holding one of the terminal hydrogens. These electrons will be attracted to the positive carbon to turn an alkane into an alkene, and an H plus will be ejected. Since the H plus initially used at the beginning of the reaction is regenerated at the end, this is called catalysis. So for organic reactions, substitutions can occur for alkanes and alcohols where an H or an OH respectively is replaced with a halogen. And in addition, a double bond is opened up. As you just saw in an elimination, an alcohol is turned into an alkene and an OH is removed. H2O is removed, rather. Finally, you can have a condensation reaction, which literally means putting two things together. The first type of condensation involves two alcohols. Your reactants, therefore, are going to be ROH and R'-OH. The product will once again be water and a new compound called an ether with the form ROR'. So if we react 2-propanol with 1-butanol, you will get water and the compound shown, which is called an ether. Ethers are oxidized hydrocarbons with bridging oxygens. To name them, you name the two individual components in alphabetical order, followed with the word ether. So alphabetically, a 1-butanol becomes a 1-butyl group. A 2-propanol, after removing the OH, becomes a 2-propyl group. So the name of this product is 1-butyl 2-propyl ether. Again, for organic reactions, a substitution replaces an H from an alkane or an OH from an alcohol with a halogen. And in addition, an alkene is turned into an alkyl halide by opening the double bond. In an elimination, water is removed from an alcohol, turning it into an alkene. And a condensation, putting two things together. We've already seen that you can have a condensation between two alcohols. You may also have a condensation reaction between a carboxylic acid and an alcohol. In this case, as mentioned, your reactants are a carboxylic acid and an alcohol, and your products are again water and another new compound called an ester. So in this case, if we react 2-propanol with butanoic acid, the product will be water and the compound shown, which is called an ester. An ester is another type of oxidized hydrocarbon. It is treated as a modified weak base. The alcohol group is named first with the suffix YL. The acid group is named last with the suffix changed to -ate to indicate the weak base. So the alcohol, 2-propanol, after losing the OH, becomes a 2-propyl group. And after losing an H+, butanoic acid becomes 1-butanoate. So the name of the product is 2-propyl 1-butanoate. In a summary of organic reactions, you have seen there are a limited number of reactions and only certain types of compounds will do certain types of reactions. So here's what you should look for. If you see an alkane reacting with a dihalide, you are looking at a substitution reaction. Your product will be an alkyl halide and an HX, and for advice, because of steric hindrance, the halogen will always attack a terminal carbon. If you see an alcohol reacting with HX, you also have a substitution. This one is easier because the H+ and the OH- will make water, and your other product will be an alkyl halide. So the advice is, always make water if you can. If you see an alkene reacting with a dihalogen. You now have a symmetric addition. The product will be an alkyl dihalide, and you will have an X on both ends of what used to be the carbon-carbon double bond. If you see an alkene reacting with HX, you now have an asymmetric addition. Your product is a simple alkyl halide. And remember, H likes H. Whichever side of the double bond has the most hydrogens will get the hydrogen, with the halogen going to the other carbon. If you see an alcohol with an acid catalyst, you now have an elimination reaction. Your product will be an alkene. This reaction is easy to spot because all you have to look for is the H plus over the arrow. If you see an alcohol reacting with another alcohol, you have a condensation reaction. Your product will be water and an ether. Again, anytime you have H's and OH's floating around, always not a bad idea to make water and put the two pieces left over together. Finally, on the same theme, if you see a carboxylic acid, which is a H plus donor, with an alcohol, you have another condensation reaction, this time making an ester, which is a modification of the conjugate weak base. And again, the H plus in the acid will go to the OH for the alcohol, and you will make water if you possibly can.